Welcome everybody, my name is Alex and this is my presentation on carbon-based fuels, where we will be discussing Canada's pioneering efforts towards reducing their greenhouse gas emissions through carbon capture, utilization and storage, also known as CCUS, while also exploring the idea and potential outcomes that stem from the peak oil theory. For the sake of this discussion, the term carbon-based fuels and fossil fuels will be used interchangeably. So first and foremost, a carbon-based fuel is a molecule whose chemical structure consists of at least one carbon atom, though most carbon-based fuels are actually chains of hydrocarbons. The carbon-based fuels pertinent to the discussion to their effects on the environment are coal, petroleum, and biofuels such as biodiesel, biogas, and bioethanol. Their energy is harnessed by reacting these hydrocarbons with elemental oxygen, which is commonly found in the air that we breathe. This is a process known as a combustion reaction. The products of a combustion reaction with the carbon-based fuel reactant will always be carbon dioxide and water, with the former commonly attributed to the global warming crisis due to its ability to retain and emit the heat found in the Earth's atmosphere. The carbon dioxide emitted through the burning of these fossil fuels has been classified as a greenhouse gas due to their contribution to the greenhouse effect in the atmosphere. Several international policies have been put into effect in hopes of reducing global greenhouse gas emissions, including the 2016 Kigali Amendment to the Montreal Protocol, the 1997 Kyoto Protocol, and the signing of the 2015 Paris Agreement. To help put this into perspective with some values, here is a snapshot of Canada's greenhouse gas emissions since the implementation of the Kyoto Protocol until 2023, and we can see that approximately 27.37% of all of Canada's greenhouse gas emissions came from the oil and gas economic sector, followed pretty closely by transport, and buildings and agriculture are usually pretty close behind as well. Of this energy, 87.1% came from fossil fuels, with a further breakdown of 41.4% coming from crude oil, 36.5% from natural gas, and 9.2% from coal sources, with the roughly 13% remaining coming from renewable energy sources such as hydroelectricity, nuclear energy, or wind and solar energy. Canada has long been a pioneer in reducing its greenhouse gas emissions through various policies, favorable geology, and technical expertise, opening the world's very first power plant with carbon capture and storage technology in Saskatchewan in 2014. However, the climate crisis continues to advance alongside dwindling resources and an increasing demand for oil, eventually leading to the day of peak oil, where global production of oil reaches its maximum before irreversibly declining. As such, the push for the decarbonization of the oil and gas sector through CCUS has become more and more prevalent as the day of peak oil approaches. So why are we so interested in capturing carbon? We've already discussed how detrimental the oil and gas sector is to Canada's greenhouse gas emissions. However, it's also important to note that the oil and gas sector contributed nearly 3.2% of Canada's GDP in 2022. As such, the incentive to discover cost-effective methods of greenhouse gas emission reduction is highly motivated in the oil and gas sector, and CCUS technologies have been found to be substantial in reducing these emissions while fossil fuel processes continue. There are three stages involved in CCUS: capturing the CO2, transporting it to a suitable geological formation, and storing it in said formation. The most common capturing process is to use liquid amines to chemically separate from the CO2 from the smokestack, which is then cooled, and the pure carbon dioxide stream is then transported into a compressor where it condenses into a fluid for subsequent transportation. So we can see this would be like the general smokestack in this flue gas cooler here. The CO2 would be absorbed up here, and then it would be sent through this thing here, and then up and through here, and then it gets compressed up into a fluid, and it gets transported up through pipelines, or trucks, or boats, or ships, or however they chose to transport it. Capture seems to be most effective directly at the emission site, which is known as point source capture, averaging a 90% capture rate. However, direct air capture technologies are becoming a topic of increasing interest due to its ability to absorb the carbon dioxide directly out of the atmosphere itself, potentially leading to net negative emissions. Though more efficient, direct air capture is significantly more expensive than point source capture because the CO2 is more dilute in the atmosphere than in the waste streams and combustion of the fossil fuels, and is therefore a little bit harder to extract. The utilization of captured carbon is essentially the idea of turning waste CO2 into a viable product. This has been classified into two principal categories: direct use and conversion utilization. Direct use, as the name implies, is the usage of the captured carbon directly into the desired area. Examples of direct use would be the carbonation of soft drinks, the use of it as a refrigerant in greenhouses to promote growth, and in a process known as enhanced oil recovery. And this is where captured carbon is injected directly into nearly depleted oil sands and fields in hopes of extracting the harder to reach oil down there due to the pressure differences. Alternatively, captured carbon may also be converted into fertilizers, biofuels, cement, nanoparticles, and many other sources to provide an economic offset to the cost of the carbon capturing process. As for carbon storage, liquefied CO2 is flowed through a pipeline to a storage facility deep underground, typically in the range of 1 to 2 kilometers below the surface of the Earth. However, the geology of this location is a very crucial factor to consider. Geologists are mostly looking for areas of very porous rock underneath the surface with a cap rock over top of it. So the porous rock would allow the liquid CO2 to seep into it and stay deep underground, while the cap rock would prevent it from re-entering into the atmosphere and coming back to the surface. This cap rock phenomenon is also what has allowed all of our fossil fuels and our hydrocarbons to remain in the Earth's crust for the millions of years that they already have. And so doing this with the carbon dioxide that we capture would just be returning it to the Earth and not allowing it to release into the atmosphere. Alternatively, there's also the mineralization of carbon dioxide upon its reaction with basalt rocks that produce carbonate minerals that prevent the CO2 from entering the atmosphere as well. Alberta's geology is really good for carbon storage, and there is actually a carbon capturing and storage facility named Quest in northern Alberta that has captured and stored nearly 9 million tons of carbon dioxide since its opening in 2012. And this diagram right here is a pretty good depiction of just one of the many CCUS processes that exist. So everything on the left side of the screen here is the carbon capture, so it can be captured from the atmosphere, hydrogen production, power stations from biomass or the fossil fuels that we've been burning, and also just heavy industry, so chemicals, cement, natural gas processing. And then these little arrows are the transport through the pipelines. It can be through trucks, boats, ships, planes. Pipelines are pretty common though. And then either the utilization is over on this side of the screen here in the fuel, chemical, and building materials industries. And then if they were choosing to store it instead of utilize it, they would put it down into these very deep rock formations in the Earth. Cool. So the peak oil theory stems from Marion King Hubbard's 1956 hypothesis that oil production follows a steep bell curve, indicative of a point of maximum production and availability of oil, followed by a steep irreversible decline where oil would become increasingly more valuable. There is large debate among publications on the theorized date of peak oil ranging from 2028 to as late as 2050. However, the ramifications of decreasing oil reserves and accessibility can have significant political, economic, and environmental impacts. Venezuela, Saudi Arabia, and Canada are the three nations with the largest oil reserves, with an estimated 530 billion barrels amongst them. Alternatively, the United States, China, and India are the countries with the highest rates of consumption of crude oil, with an estimated 38.62 million barrels a day combined. At this rate, Venezuela, Saudi Arabia, and Canada's entire oil reserves would be depleted by just the US, China, and India's oil consumption in a little over 37.5 years, in around the year 2060. The environmental impact as we approach the day of peak oil would be substantial. As oil reserves deplete, the extraction processes from the oil fields and sands would become exponentially more energetically demanding. This would result in more money being put into technologies to extract this harder to reach oil, similar to the enhanced oil recovery process mentioned previously, but with significantly less product yield. This would then create a net negative energy use, and the natural world's resources would just continue to deplete. Further, the lack of availability could create political tension and unrest. Historically, full-scale wars have erupted over access to oil, including the Iraqi invasion of Kuwait in 1990 and the Iran-Iraq war across the 80s decade. As a consequence of war, the global economy and access to the resources that are being fought over would begin to dwindle. The everyday person could potentially see dramatic price increases in the price of gasoline, natural gas, and a large-scale transition to electrically powered vehicles in hopes of extending the lives of these oil reserves. To conclude, the burning of carbon-based fuels are contributing to an increasing level of CO2 in the atmosphere. CO2 is the main culprit alongside other greenhouse gases in the global warming phenomenon on climate change. As such, the carbon capture, utilization, and storage technologies and policies pioneered by Canada are crucial in reducing global greenhouse gas emissions in hopes of slowing the rates of global warming. CCUS also addresses the problem of oil being a finite, non-renewable source of energy through practices such as enhanced oil recovery. Some limitations in the research include cost-effective measures as well as limited technologies to incorporate direct air capture from the atmosphere to drive net zero emissions. Furthermore, the University of Regina's Faculty of Engineering and Applied Science offers a master's program in carbon capture, utilization, and storage as an opportunity for career advancement or to further bring the narrative back to the ever-changing climate crisis.